Section 12.6, OR and problems. In this section, we're going to focus on compound probability. Compound probability can be written one of two ways. It can be written with the word or. It can also be written with the word and. We also want to decide at the end whether we're dealing with an independent or a dependent event. In this section, we learn how to solve compound probability problems that contains the word and or. We're going to try to do this without constructing a sample space so that we don't have to make all the tree diagrams and the lists of numbers. OR probability. The OR probability problem requires obtaining a successful outcome for at least one of the given events. So, if you're looking for the probability of A or B, to determine the probability of A or B, you're going to use the following formula. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Let's look at an example. Each of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is written on a separate piece of paper. The 10 pieces of paper are then placed in a hat, and one piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or a number greater than 6. So there's two ways that you can do this. You could do this with a Venn diagram and simply count, or you could do this with the formula. So let's look at the Venn diagram option first, and you can decide which one you like best. So if we did the Venn diagram, we would draw a rectangle for a universal set. We would draw one circle. This circle is going to represent even numbers. We're going to draw a second circle, and the second circle is going to represent numbers greater than 6. Okay, so even numbers and numbers greater than 6. Okay, so let's start with the number 1. Number 1 is not even. It is also not bigger than 6, so it goes outside. The number 2 is even, but is not bigger than 6. The number 3 is odd and not bigger than 6, so outside. The number 4 is even, but not bigger than 6. 5 is odd and not bigger than 6. 6 is even and not bigger than 6. 7 is odd and bigger than 6. 8 is even and bigger than 6. 9 is odd but not bigger than 6. 10 is even and bigger than 6. So if you have your Venn diagram filled in, the question said, determine the probability that the piece of paper selected contains an even number or a number greater than 6. So you have 3 items that are even, you have 2 items that are even and bigger than 6, and you have 2 items that are bigger than 6. So if you added all those together, 1, 2, 3, 4, 5, 6, 7, there's 7 out of 10 possible numbers that are even or bigger than 6. Some people would prefer to do it with the formula because they don't like drawing the Venn diagrams. So if you want to do it with the formula, in order to calculate the probability that you are even or greater than 6, you first have to find the probability that the number is even plus the probability that the number is greater than 6 minus the probability of both. Okay, so if we look at our numbers 1 through 10, what's the probability of being even? 2, 4, 6, 8, 10. 5 out of 10 items are even. What's the probability of being bigger than 6? 7, 8, 9, 10. 4 out of 10 items are bigger than 6. What's the probability that you're both even and bigger than 6? So that would be the 8 and the 10. So 2 out of 10 are both. And then remember, when you add fractions, you just go straight across the top. 5 plus 4 is 9. 9 minus 2 is 7 out of 10. So you're allowed to do the problems either way you want, as long as you can keep it straight. Next is the definition mutually exclusive. Two events A and B are mutually exclusive if it is impossible for both events to occur simultaneously. If two events are mutually exclusive, then the probability of A and B simultaneously happening is 0. So if that is the case, then the addition principle gets even easier. The addition principle of the probability of A or B would simply become the probability of A plus the probability of B. But remember, that is only the case if the events are mutually exclusive. Let's look at an example. One card is selected from a standard deck of playing cards. Determine whether the following pairs of events are mutually exclusive and determine the probability of A or B. So first, A is the probability that you get an ace, and B is the probability that you get a 9. So it's impossible to have a card that is simultaneously an ace and a 9, so this event would be considered mutually exclusive. So all you would need to do is find the probability of an ace, the probability of a 9, and add those two probabilities together. Now remember, there are 4 aces in a deck, and there are 52 cards in a deck. There are 4 9s in a deck, and there are 52 cards in a deck. So if I added those together, that probability would be 8 out of 52. And then remember to always reduce your fraction. Both of these numbers are divisible by 4, so your probability would be, 8 out of 13. The probability of event A is an ace, and the probability of event B is a heart. These are not mutually exclusive because you can have an ace of hearts. So if you're going to use your formula, you would have to find the probability of an ace plus the probability of a heart, and then deduct out the probability of an ace of hearts. So the probability of both. So remember, the deck has 4 aces out of 52 cards. The deck has 13 hearts out of 52 cards, but there's only 1 ace of hearts. So the probability of getting an ace or a heart would be 4 plus 13, which is 17, minus 1 would be 16 out of 52, and then you would have to divide both of those by 4 to reduce your fraction. Your probability would be 4 out of 13. Question C. The probability of getting a red card or a black card. These events are mutually exclusive because no card in the deck is simultaneously red or simultaneously black. So you could just find the probability of red and the probability of black, and you could add those two probabilities together. So half of the deck is red, so 26 out of 52 cards is red. Half of the deck is black, so 26 out of 52 cards are black. So 52 out of 52 cards are red or black, so that's a 100% probability. Last question. The probability event A is a picture card. The probability event B is a red card. These are not mutually exclusive because you could have a queen of hearts, a queen of diamonds, a jack of hearts, a jack of diamonds, a king of hearts, a king of diamonds. So you are going to have to use your special formula. So the probability of a picture card or a red card, you have to find the probability of a picture card plus the probability of a red card minus the probability of red picture cards. Okay, so picture cards are jacks, queens, and kings, and there's 4 suits, so there's 3 in each suit, so that would be 12 picture cards out of 52 cards. The probability of red, remember half the deck is red, so 26 out of 52 would be red. And then the probability of red picture cards. So there's a jack, queen, king of hearts, and a jack, queen, king of diamonds. So that's 6 out of 52 that are both red and picture cards. So if you add 12 plus 26 minus 6, you will get 32 out of 52 And then, of course, you have to reduce this to 8 out of 13. The other type of problem you're going to encounter are AND problems. The AND probability problem requires obtaining a favorable outcome in each of the given events. To determine the probability of A and B, you need to find the probability of A times the probability of B. Since we multiply to find the probability of A and B, this formula is sometimes referred to as the multiplication formula. When using the multiplication formula, we always assume that event B has occurred when calculating event B, because we're always determining the probability of obtaining a favorable outcome in both of the given events. So let's look at example 5. 2 cards are selected without replacement from a deck of cards. Determine the probability that 2 spades will be selected. Okay, so the probability of 2 spades. First thing we need to do is find the probability of selecting 1 spade, and then multiply by the probability of the second spade. Okay, so keep in mind that there are 52 cards in the deck, and that 1/4 of the deck is spades. So 13 out of 52 cards are spades. And then remember that event 1 occurred. So you have taken one of the spades out of the deck. That means only 12 spades are left and only 51 cards are remaining. So you can multiply across the top, multiply across the bottom, reduce your fraction. Your probability of 2 spades in a row is 1 out of 17. Event A and Event B are considered independent events if the occurrence of either event in no way affects the probability of the other event. So rolling a dice and tossing a coin are examples of independent events. Let's look at example 6, which is an independent event. 100 people attend a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement, and each will be awarded 1 door prize. Are the events of selecting the 3 people who will be awarded the door prize independent or dependent events? In this case, the events are dependent, since each time one person is selected, it's going to change the probability of the next person being selected. So in the first selection, the probability is 1 out of 100. If that person is not selected, then in the second selection, the probability is 1 out of 99. And in the third selection, it's 1 out of 98. So notice how the denominator changes? That would be considered a dependent event. In general, any experiment in which 2 or more items are selected without replacement is going to be considered a dependent event.